Hello, everyone. I got the urge to go to Target and buy Doom for my Nintendo Switch and blast some demons. Has anyone played Doom for Nintendo? Anyone played the new Doom that came out fairly recently? Like the Doom reboot? And if so, is it fun? Because I'm thinking about blasting some demons this afternoon. It's fun. All right, I'm sold. Sometimes I just want to like mindlessly play a game. You know what I mean? Not even like what's another game I got? I got like uh, Marvel Ultimate Alliance where the game is like so easy. You just like mash the same button the entire time. You're just like psh, 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 and you just go around and beat the crap out of people just like psh, psh, psh. Pretty fun. Okay. So I think we've got enough to get started. So this is our review of the last stuff that we covered in semester one. I want to remind you that if you have any late work, you need to let me know via a Canvas message by Wednesday if you want it to be graded. I generally do not let students redo old assignments for credit. If you didn't do the assignment at all, you can get some credit no matter what. But if you have a D or an F, I will let you redo old assignments to get your grade up to the C level. Okay? Because I believe that everyone should be above sea level, at or above sea level. Okay? Because I don't want you to drown. Okay. Your final exam is due on Friday. Okay. So we finished. Excuse me. On Friday, we finished talking about gravitational fields. So now we're going to talk about the third triad stuff. So the first concept I'm going to discuss is called center of mass. And center of mass is essentially the average position of the mass in a system. Or you could think about it as the balance point. Okay. So there's a formula we learned for center of mass. So typically I denote center of mass by XCM. And it's equal to M1 X1 plus m2x2 plus m3x3. So here, m1 is the mass of the first object, x1 is the position coordinate of the first object, plus same thing for the second, same thing for the third, plus dot, dot, dot. However many masses you have, divided by the total amount of mass. Okay? Now, if you have an object that's asymmetrical, the center of mass is not going to be the geometrical center. Okay? But if you have a uniform symmetrical object, the center of mass will be the center. So, for example, what if you had a rod? Okay? And the rod goes from x equals 0 meters to x equals 5 meters. Okay? So, and it's a 15 kilogram rod. So where is the center of mass of this? Well, because it is a uniform rod, its center of mass will be in the middle at 2.5 meters. Okay? So what if I had a system that consisted of this rod and then a 20 kilogram mass that is placed at the origin? And I wanted to find the center of mass. Okay? Well, it would be m1 times x1. So it's going to be 20 times this mass is at location 0 plus 15 times the position of this rod. So the position that you want to use for the rod is the position of its center of mass. Okay? So to calculate the center of mass of the system of two objects, I use the center of mass of each individual object. So this is going to be plus 15 times 2.5 divided by the total amount of mass, which is going to be 20 plus 15, 35. So whatever that number ends up being, it's not really important. So that is center of mass. Okay? Then we discussed torque. Torque is a twisting force. So the, I feel like this is not focused very well. Let's see. Maybe a little bit better. So what you want to imagine is, suppose you have some blob like this, okay, and the blob is pinned at a certain location, okay, and somewhere else you apply a force on the object, okay. So here's a force that you're applying, and the force is applied at an off-centered location, okay. So we can see that if you pin it on this side and if you push it right there, it's going to rotate counterclockwise, all right? So what we want to do is we want to draw a line segment from the pivot point to where the force is applied, and the length of that line segment is called r, okay? And then once we've drawn that line, we can figure out what is perpendicular to that line and what is parallel to that line. Okay, so we take the force and we break it up into components. One component is perpendicular and the other component is parallel. Okay, so that breakdown is accomplished with trigonometry. Okay, and then the torque is F perp times R. All right. If the torque tends to rotate the object counterclockwise, we consider that to be a positive torque. And if it is going to tend to rotate the object clockwise, that is a negative torque. Okay, so this right here would be a positive torque because this force is tending to rotate the thing counterclockwise. So your net torque is simply the sum of the individual torques on the object. Okay. One of the things that we talked about was that gravity exerts a torque. Okay. So there is a torque due to gravity. And the gravitational force is mg. Okay. And so we take the perpendicular component of mg and we multiply it by r, where r is the distance from the pivot point to the center of mass of the object. So what that means is that the gravitational torque acts as if it were located at the center of mass. The gravitational force acts as if it's located at the center of mass. So what if we have this beam up here? So we have this beam, and it extends from 0 to 5 meters. Okay. And what if we pinned it at x equals 1 meter? So there's the pivot point. All right. And I want to know, what is the gravitational torque on this thing? Okay, it's a 15 kilogram rod. Remember, it's the same rod as this one. So 15 kilograms means that mg is going to be 150. All right. Now, what is RCM? Well, it is the distance from the pivot point to the center of mass, which is in the middle here at 2.5 meters. So the distance from that pivot point to the center of mass, that distance is going to be 1.5 meters. So my RCM is 1.5 meters. Okay? So that means that my gravitational torque in this case would be 225 Newton meters. So I think it's fairly obvious here that that this gravitational torque is going to cause the rod to rotate in the clockwise sense. And so for that reason, the gravitational torque is negative. All right, so that's torque. And then we talked about rotational inertia, which is denoted by I. And so the rotational inertia is measuring how difficult it is for an object for you to change its angular velocity, how fast it's spinning. So things that have a large rotational inertia, it's difficult to start them spinning, and it's difficult to stop them spinning, because once they get going, they just want to keep spinning. Okay? So the formula for inertia is sum over mr squared. Okay? Where r is the distance from the axis of rotation. Okay? So it depends. So the distance from the axis of rotation depends on where the axis is, which direction it's pointed. So we have to worry about that. So for example, what if I had two masses right here and right here? Okay, so maybe this is M1 and this is M2. All right, and maybe they're separated by a distance d. Okay, now what if this is the axis of rotation? Okay, in that case, because both masses are on the axis of rotation, they both have a distance r equals 0. So in this case, the inertia would be 0. That's an important thing. If the mass is on the axis of rotation, it does not contribute to the inertia. Okay? You might want to know that for the final exam. If you have an axis that's right here, okay, maybe this distance right here is r. What if you rotated about that axis? What would the inertia be? Okay, in that case, the inertia would be the inertia of the first object, m1 times, now how far is that object from the axis of rotation? Well, it's this far is r, and that far is d, so it's r plus d from the axis of rotation squared, plus the contribution from this mass, which is m2, times its distance from the axis of rotation is just r, like that. Okay? So this is how you calculate the inertia for a system of point masses. So you have a point here, you have a point there, you have a point here. But what if you have an extended object where that picture doesn't really make sense? So for example, what if you have a disk? Yeah! A solid disk. Or what if you have a solid sphere? Or what if you have a hollow sphere? Something like that. Okay? And in these cases, the rotational inertia is obtained from calculus. Okay? This is not a calculus-based class. So anytime you have something that's spinning that is an extended object such as this, I would just give you the formula. Okay? So for example, and you don't need to write this down because I will tell you on the exam when you encounter these objects. I will say it's a solid sphere. Solid spheres have an inertia of 2/5 mr squared. Okay. Solid disks have an inertia of 1/2 mr squared. Hollow spheres have an inertia of 2/3 mr squared. So the inertia depends on the geometry of the shape. Okay. We went on to discuss angular kinematics. Delta theta is known as the angular displacement. Okay, so that's basically how many radians or how many degrees does something turn. Okay. Sorry, I just saw a question about, I'm assuming the "oh God" comment is because I sneezed. And the y is I equals 0. Because r is your distance from the axis of rotation. So if you are on the axis of rotation, your distance from it is 0. All right? It's like if you're touching something, if I touch the camera, my distance from the camera is 0. Okay, so if you are on the axis of rotation, such as these two masses in this case, if this is my axis of rotation, it's touching both of those masses. So the r values are 0, which means that when I do this sum, I would have m1 times 0 plus m2 times 0, which is equal to 0. Okay, so then we have omega, which is the rate of change of angular position, and that is the angular velocity. And then we have alpha, which is the rate of change of angular velocity, which is called the angular acceleration. So if, that's a big if, alpha equals a constant, because you could have situations where the angular acceleration is changing. You know, your wheels are spinning at a constant rate so that the angular acceleration is 0. Then they start spinning faster, so you have a positive angular acceleration. Then they start spinning slower, so you have a negative angular acceleration. Stuff like that. But if it's constant, we have these equations of angular kinematics, okay, which are the same as the equations of linear kinematics, just translated into angular variables. So delta theta equals omega naught being the initial angular velocity, times time, plus 1/2 alpha t squared. Omega final equals omega initial plus alpha t. Omega final squared equals omega initial squared plus 2 alpha delta theta. Now, angular kinematics is pretty much the only spot in this course where we use radians instead of it uses radians instead of degrees, okay? There is a question on the final where I ask you to calculate the number of times something turns in revolutions, not in radians. And so for that question, I want to make sure you know that 1 revolution is equal to 2 pi radians. Okay? So this delta theta is going to spit out in radians. So if you wanted to convert that to revolutions, you'd have to divide it by 2 pi. So there's a question in the chat. Does initial potential energy plus kinetic energy equal final potential energy plus kinetic energy even when it's rotational? Yes, it does. Okay, so then I would, then we talked about Newton's second law. For rotation. Zip. Okay. And so what Newton's second law for rotation says, it's very simple. It says that the net torque is equal to the inertia times the angular acceleration. So if something has a net torque of 0, it's going to keep spinning at the same rate forever. It's going to have 0 angular acceleration. It'll just keep spinning at the same rate. If something does have a net torque, it's either going to start spinning faster or start spinning slower. And the rate at which it does that depends on the inertia. Okay. Typically, this equation is used, the way that it's used is the net torque and the inertia. So you solve for the angular acceleration, and then you plug that into the equations of angular kinematics. Okay. So we then talked about angular momentum, which is denoted by L. And so there are kind of 2 types of angular momentum. They're really the same thing, but it's a useful division. One is called the orbital angular momentum. So the orbital angular momentum has to do with an object as a whole orbiting about another thing. So if we think about a tetherball is orbiting the tetherball pole as a whole. So that would have orbital angular momentum. If we talk about something like the Earth has orbital angular momentum because it's orbiting around the sun. The moon has orbital angular momentum because it's orbiting about the Earth. Okay? So the formula for orbital angular momentum is object's mass times its speed times the radius of its orbit. Then you also have spin angular momentum. So spin angular momentum is the angular momentum of something that is rotating, spinning in place, okay? And that is I times omega. So inertia times angular velocity. Some objects have both of these. So if we think about the Earth is orbiting the sun, and as it orbits, it's spinning about its axis. So the total angular momentum of the Earth is going to be the sum of these two. Okay. So why is angular momentum a useful thing to study? Well, if you have an isolated system, then the total amount of angular momentum that you start with is equal to the total amount of angular momentum that you end up with. So angular momentum is conserved. So for example, if you have a spinning object, maybe you have a spinning object that is changing shape. So then your initial angular momentum is I initial times omega initial. Your final angular momentum is I final times omega final. Okay, so the change in the inertia of the object results in a change of the spin rate. So lastly, we talked about rotational kinetic energy. So your total kinetic energy is broken up into two parts. There is a translational kinetic energy, which is the kinetic energy, the energy of motion associated with going from point A to point B, so moving locations. And then you also have a rotational kinetic energy, which is the kinetic energy of your spinning in place. Okay? So an object could have just one of these, or it could have both. So let me give you an example. If you have something like a block, blocks are rectangular, so they're usually not spinning. Okay? So if a block goes from place to place, it's probably just translating. If you think about something like a toilet paper roll, okay, and you pull down on the toilet paper roll as a whole does not move. The roll stays put, but it starts to spin in place. Okay, so the toilet paper roll would have rotational kinetic energy, but not translational kinetic energy. You can have both. Things like the Earth is translating through outer space, and it's spinning as it does that. Okay, so at any rate, the formula for translational kinetic energy is 1/2 mv squared, and for rotational kinetic energy, it's 1/2 I omega squared. Okay. Now, most of the time, the translation speed and the rotation rate are completely unrelated. So, for example, the Earth, the rate at which the Earth spins has nothing to do with how long its speed through outer space. Okay? But sometimes you have an object that is rolling without slipping. Okay? So if you have something like a wheel, how fast the wheel is rotating is directly related to how quickly the wheel goes forward. Okay? And so the equation that relates those two is V equals omega R. So the faster you spin, if you're rolling, the faster you're going to be moving forward. Okay? And so in that case, we can combine these two terms because now omega is related to the speed. So we can combine the two terms, and what we get is the kinetic energy of rolling which is 1/2 mv squared times the quantity 1 plus I over mr squared. Okay? Now this I over mr squared, that comes from, so typically the thing that's rolling is going to be some extended object. So, it might be a disk, okay? And if it's a disk, then I would give you this formula. I'd say inertia for a disk is 1/2 mr squared. So from this equation, you can see that I over mr squared is 1/2, okay? If you have a solid sphere that's rolling, you can see that I over mr squared is 2/5. If you have a hollow sphere that's rolling, you can see that I over mr squared is 2/3. So this I over mr squared is determined by the shape of the rolling thing. Okay? By the shape of the rolling thing. So how is this kinetic energy of rolling used? It is used most often in conservation of energy problems. So you would have some rolling object, and the rolling object has an initial rolling kinetic energy, and it has an initial gravitational potential energy. And then that becomes the final rolling kinetic energy and the final gravitational potential energy. Okay, so that's how you would use, so you can use this as a form of energy in conservation of energy problems. Okay? So that completes my review. I'm just going to check in with you guys in the Zoom room, make sure everyone submits attendance, and see if you guys have any questions, and then I'll be probably letting you go